In today's lecture, we will be covering main group chemistry, groups 13 to 15. We have already covered the S block, so we will be taking a look at the first half of the P block, as shown here. Starting with group 13, they're also known as the trials, and this group contains mainly metallic elements except boron, which is classified as a metalloid. So aluminum, gallium, indium, and thallium all show classic metallic properties. They have a general electronic configuration of noble gas Ns2, Np1. So these are the first group of elements to start filling the p orbitals. The most common oxidation states are +3 for boron, aluminum, and gallium, while thallium is more commonly +1. Indium is more commonly +3, but +1 isn't uncommon either. Group 14, or the tetrails as they are also known, are a diverse group of elements that include the nonmetal carbon as well as metals and metalloids. As you go down the group, the elements become more metallic in character, with silicon and germanium generally classified as metalloids, and tin and lead generally classified as metals. Group 14 elements have a general electronic configuration of noble gas Ns2, Np2. The most common oxidation states are +4 for silicon and germanium, +2 for lead, and tin can adopt +4 or +2. Carbon, however, is a huge outlier and can have oxidation states anywhere between -4 and +4. The last group we'll look at today will be group 15, otherwise known as the pnictogens. This group contains nonmetals, metalloids, and only one metal, bismuth. Nitrogen and phosphorus are nonmetals, while arsenic and antimony are metalloids. The pnictogens have a general electronic configuration of noble gas Ns2, Np3, so all of the p orbitals are half filled. Common oxidation states include -3 for the first three elements, as well as +3 and +5 for the first four elements. It should be noted that bismuth only really adopts the +3 oxidation state and not +5. The inert pair effect is an important phenomenon when looking at p-block chemistry. It refers to the tendency for the 6s electrons to resist ionization, especially in groups 13 to 16. It is also likely apparent in group 17, but we will see next lecture why we don't know that definitively. It is also seen to a lesser degree for the 5s electrons. How does this relate to the common oxidation states mentioned in the previous slide? You may have noticed a bit of a trend for the heaviest elements of the first three groups of the p block. They all adopt oxidation states 2 lower than the rest of their group. +1 for thallium, +2 for lead, and +3 for bismuth. Similarly, the second heaviest elements of these groups can adopt the same oxidation states, +1, +2, etc., but they also adopt the one more common for their group, +3, +4, etc. So what causes the inert pair effect? This can be traced to the d and f orbitals being very poor at shielding nuclear charge. The reason why they are so poor at shielding nuclear charge is almost the exact same as the reason why p orbitals are bad at shielding nuclear charge. This will probably make more sense in the next section of the course when we look at the transition metals. Because the d and f orbitals are so bad at shielding nuclear charge, we see what's called the d and f block contraction. In this case, the d block contraction is what we're concerned about with respect to the inert pair effect. And the d block contraction is where the atomic radius does not increase as much as expected down a group in the p block. This is most pronounced in group 13. So the poor shielding of the d electrons, along with the increased number of protons in the nucleus, leads to a very large effective nuclear charge for the valence electrons in the p orbitals. You also need to remember that the s orbitals penetrate close to the nucleus. For the 6s electrons, this is particularly important because of the large amount of positive charge in the nuclei of very large atoms. This causes what are called relativistic effects, which make the 6s electrons more inert than expected. One way to conceptualize relativistic effects is if you think of electrons as orbiting the nucleus, kind of like planets orbiting the sun. They need to have a certain amount of momentum in order to prevent them from getting pulled in. The attractive forces in this case would be electrostatic rather than gravitational. Because the 6s electrons penetrate so close to the nucleus, and there is such a large positive charge in the nucleus of these very heavy atoms, in order to resist the electrostatic attraction to the nucleus, the electrons need to have velocities approaching the speed of light to prevent from collapsing into the nucleus. At such high speeds, however, the electrons behave like massive particles, which makes them very hard to remove. As such, the p electrons can be oxidized, but the 6s electrons are very inert. The 5s are a little more reactive because the atoms in row 5 aren't nearly as large and don't have as many protons in the nucleus. This explanation of relativistic effects is very imprecise, though, because electrons don't orbit the nucleus like planets. They don't really have velocities per se, but it is a good way to conceptualize the inert pair effect. Now moving on to group 13 specifically, we will look at boron first and then move down the group. Elemental boron is a metalloid, so it exhibits both metallic and non-metallic characteristics. The classification of metalloids is somewhat subjective, especially for some borderline cases. On the right is a picture of the p block with the traditional metalloids highlighted in green. Both aluminum and carbon are sometimes classified as metalloids, as are selenium and polonium. I'm not overly picky about the semantics of what is and is not a metalloid, but it is important to be aware of which atoms may be considered metalloids. So going back to boron, it is a hard, shiny solid in its elemental state. It has a high melting point and boiling point, but it also acts as an insulator. Boron forms 3 covalent bonds quite readily, or becomes sp2 hybridized in organic chemistry terms. Elemental boron can be oxidized by strong oxidants, like fluorine gas, to form compounds like boron trifluoride. 3-coordinate boron, however, does not have a stable electronic configuration. It only has 6 valence electrons. 1p orbital remains completely empty. What does this mean about boron's reactivity? What kinds of compounds have low energy LUMOs? It means that 3-coordinate boron acts as a Lewis acid. When it forms an adduct, it adopts a noble gas electronic configuration. The Lewis acidity of boron compounds can be changed depending on what substituents boron is coordinated to, so depending on what those R groups are. For example, borane, or BH3, is a soft Lewis acid, while boron trifluoride is a hard acid. 4-coordinate boron is also quite common, usually in the form of anions. The formation of these tetrahedral anions is driven by the Lewis acidity of boron and the stability associated with a full octet. Shown below are some examples of some simple boron anions, and you can imagine them being formed through a reaction of the 3-coordinate boron species with the corresponding anion, so fluoride, chloride, etc. Tetrafluoroborate, in the middle there, is a very common anion used in transition metal chemistry because it is non-coordinating. Boranes, or compounds with BH bonds, are commonly used as reductants and show some interesting chemistry that is a little bit unique. Boranes come in many forms, one of the most common being borohydrides, like sodium borohydride, which is used as a reductant in organic chemistry. Free borane, or BH3, is not that stable by itself, due to the Lewis acidity of the boron center, and it will reversibly dimerize to form other tetrahedroboranes, one of which is shown below. This binding mode should be somewhat familiar as we covered it in last class. Here are the orbitals that overlap to form this interaction. Similar to beryllium in the +2 oxidation state, boranes can form 3-center 2-electron bonds to form dimers and larger clusters. This allows boron to achieve a full octet, so there is a significant driving force to form these types of interactions. The last class of boron-containing compounds we will look at are borates. Boron forms very strong bonds with oxygen, so boron halide bonds are prone to substitution. Either water or alcohols will substitute weaker boron-halogen bonds, and sometimes boron-carbon bonds can be substituted too. So here's just a general reaction scheme. Moving on to aluminum, the first metallic triol. It is a soft, pliable metal in its elemental form that reacts with both acids and oxygen. You're probably most familiar with this metal in the form of aluminum foil. The reaction of aluminum with acid is a redox reaction where aluminum gives up 3 electrons and generates hydrogen. Aluminum also reacts with oxygen, somewhat similar to beryllium. Also similar to the atom it has a diagonal relationship with, aluminum forms a passivating aluminum oxide layer upon reacting with oxygen that prevents the rest of the metal underneath reacting with air. We can see that elemental aluminum is quite reducing, with a reduction potential of minus 1.66 volts. By giving up 3 electrons, aluminum adopts a noble gas electronic configuration, so it makes sense that the metal would be fairly reducing. There are some similarities between boron and aluminum in that they both form covalent 3-coordinate sp2 hybridized compounds that are Lewis acidic because of an empty p orbital. They both readily form tetrahedral anions, as shown here, and they both form hydrides, although for aluminum they do not bridge. Lastly, they both form strong bonds with oxygen, and aluminum halides as well as aluminum carbon bonds will readily react with alcohols and water to form stronger aluminum-oxygen bonds. Aluminum forms stronger bonds with oxygen than boron, though, because it is a harder acid, which means it forms weaker and more reactive bonds with softer Lewis bases like hydrides, carbon, and most halides. For the rest of group 13, we will look at them together. As you go down the group, the elements become more and more metallic, mainly due to the lower ionization energy, lower electronegativity, and lower electron affinity. As such, their interactions become more ionic in character. Although gallium and indium halide will still form Lewis acid-base adducts similar to aluminum and boron, what's different is that they can also form 5 and 6 coordinate species in addition to tetrahedral anions. Down the group, the +1 oxidation state also becomes more stable. Looking at the reduction potential of gallium 3 plus cations to gallium 1 plus cations, we can see it is fairly negative, so this would not be a favorable reaction. This tells us in a somewhat roundabout way that gallium in the +1 oxidation state is not really stable. For indium, we can see that the reduction potential is less negative, so the +1 oxidation state is more stable. And for thallium, the reduction potential is quite positive, higher than actually even oxygen. This tells us that the reduction of thallium +3 to +1 is very favorable, and that thallium +3 is unstable. Why is thallium in the +1 oxidation state so stable? It is because of the 6s electrons. Due to the inert pair effect, they are much less prone to ionization than would be expected. And all the reasons for that we explained earlier in the lecture. Now moving on to group 14, we will first take a look at carbon, which displays unique reactivity when compared to the rest of the tetrals. Elemental carbon has several different allotropes, or different physical forms of the same element. One form you should be very familiar with is diamond, which is very hard, very brittle, and acts as an insulator. If you look at the structure, you can see every carbon atom is in a tetrahedral environment, which gives diamond its characteristic durability. This type of crystal structure is called a zinc blende structure. The second allotrope is graphite, which is essentially 2D aromatic sheets stacked one on top of each other. This allows the sheets to slide easily across each other, which is why graphite can be used as a lubricant. It's also why it's so soft. Along the planes of the sheets, graphite can conduct electricity, which is why carbon sometimes is classified as a metalloid. Single sheets of graphite can be separated, and these single sheets are called graphene. They have interesting properties in of themselves, which can be different than bulk graphite. Elemental carbon can also form nanotube structures, which can be considered rolled up sheets of graphene. Sometimes they are single tubes, as shown here, and sometimes there are multiple tubes nested in one another. They show similar properties to graphite and graphene, except they conduct electricity in one dimension along the tube. The last form of elemental carbon we will look at are Buckminster fullerenes, or buckyballs. You can think of these as aromatic sheets curved into balls. These can be used to store ions inside of the cage, as shown here. With respect to covalent compounds containing carbon, we will not cover them in this course because you can simply refer to your organic chemistry notes. It's important to know, though, that carbon displays the most diverse chemistry of any atom because it can form 4 bonds and adopt oxidation states between -4 and +4. When assigning oxidation states to carbon, remember to look at electronegativity values as a bit of a guide, and also remember that C-C bonds split electrons evenly. In addition, carbocations are somewhat similar to boron in that they are sp2 hybridized species with an empty p orbital. This makes carbocations very strong Lewis acids. Silicon is somewhat similar to carbon, but we will see some very distinct differences that make carbon chemistry so unique. Elemental silicon has a zinc blende structure where each silicon atom is in a tetrahedral environment. This makes silicon crystals very hard and brittle, and they have very similar structures to diamond. Silicon is classified as a metalloid because it has a shiny appearance and it has semiconductor properties. We will briefly review semiconductors on the next slide. Like carbon, silicon can form 4 covalent bonds, but it generally adopts the +4 oxidation state. Why don't we see the same variety of silicon compounds as carbon compounds? It has to do with the difference in electronegativity between silicon and carbon, where silicon is less electronegative. It also has to do with their relative bond strengths. In this table, we can see the relative bond strengths in kcal per mole of a variety of tetrals, including carbon and silicon. The first thing that jumps out is that carbon is the only element of this group to form double and triple bonds with itself. We will see on the next slide why this is the case. If you look at the silicon-hydrogen and carbon-hydrogen bond strengths, you can see that the carbon-hydrogen bonds are significantly stronger and are more stable than either the CO or C-chlorine bonds. Silicon-hydrogen bonds, on the other hand, are significantly weaker than the silicon-oxygen and silicon-chlorine bonds. We will see in a couple of slides how this influences reactivity. You may also notice that silicon-silicon bonds are fairly weak, which is why we don't see many silicon-based analogs of organic compounds. When looking at CO double bonds, in comparison to CO single bonds, you can see that CO double bonds are thermodynamically favored over 2 CO single bonds. Silicon-oxygen double bonds in contrast, are much weaker and less stable than two silicon-oxygen bonds, which is why we don't see many silicon-oxygen double bonds in chemistry, almost none. Lastly, if we look at the bond strengths of carbon-chlorine bonds and silicon-chlorine bonds versus carbon-oxygen bonds and silicon-oxygen bonds, we can see that there is a much larger driving force to form silicon-oxygen bonds, which we will see in a couple of slides. These are all the reasons why carbon and silicon chemistry are so distinct from one another. Also, due to the lower electronegativity of silicon, it is much more prone to nucleophilic attack as compared to carbon. This, coupled with accessible d orbitals and silicon's larger size, explains why silicon hydrogen and silicon chlorine bonds are more reactive than the corresponding carbon-based bonds, both kinetically and thermodynamically. So we saw in the table in the previous slide that silicon chlorine and silicon hydrogen bonds are less stable than silicon oxygen bonds. This is a thermodynamic argument for some of the reactions we will see in the next slide. We also learned that the larger silicon atom and its accessible d orbitals makes those bonds less kinetically stable. What do I mean by this? Well, when carbon undergoes a nucleophilic attack, it goes through a 5-coordinate transition state, like this. So here are your groups on carbon. Here is your leaving group. And here's your incoming nucleophile. So this is a transition state. Silicon, however, is larger than carbon, so it can fit 5 substituents around it. Also, silicon can form 5 bonds because it can sp3 hybridize. So instead of forming a high-energy 5-coordinate transition state, silicon can form a much lower 5-coordinate intermediate. So here, very similar, would be your silicon with its substituents. Here would be your leaving group. Here would be your nucleophile. But this species here is not a transition state. It would be an intermediate, and intermediates tend to be much lower in energy than transition states. This ultimately speeds up nucleophilic attacks and makes silicon more prone to substitution reactions. So not only is there a larger thermodynamic driving force to replace silicon halide bonds, say with a silicon oxygen bond, but there is also lower barriers to undergoing a nucleophilic attack because silicon can form a much lower energy 5-coordinate intermediate rather than forming a 5-coordinate transition state. The large size of silicon also makes silicon double and triple bonds unstable. So when you're looking at a carbon-carbon double or triple bond, you have your sigma bond here, then your pi bond is formed by overlap of p orbitals. Because the carbon atoms are small, they're relatively close together, so you get good overlap between these p orbitals. Silicon atoms, on the other hand, are much larger and their orbitals are more diffuse. This makes silicon-silicon sigma bonds significantly longer, right here. So the silicon atoms are farther apart. Then when you look at the p orbitals on silicon, because they're farther apart, these two atoms, you don't get effective overlap of those orthogonal p orbitals, which prevents double bond formation. Similarly, silicon-oxygen double bonds are much weaker because there is poor overlap between the silicon and oxygen p orbitals for these exact same reasons. So I've teased how these properties influence the reactivity of silicon compounds. Silanes and silyl halides are unstable in the presence of water and oxygen, whereas CH bonds and CCl bonds are stable with respect to water and oxygen under normal conditions. Silane will react with oxygen to form silica, because this reaction is both kinetically and thermodynamically favorable. You can burn methane in air, but you need a lot of energy to start the reaction. Similarly, tetrachlorosilane reacts readily with water to form silica and acid. Carbon-chlorine bonds, in comparison, don't react with water without forcing conditions. Now at this point, we will look very briefly at insulators, semiconductors, and metals because you should be aware of how their different electronic structures influence their conducting properties. Shown here is a single atom's HOMO and LUMO orbitals. If two atoms are bonded together, you now double the number of frontier orbitals. As you progressively add more, and even more atoms bonded together, similar to a crystal of silicon or diamond, you can see that there are so many orbitals overlapping together that you form bonding and anti-bonding bands. The bonding orbitals are filled with electrons and are called the valence band, while the anti-bonding orbitals are empty and called the conduction band. In order to conduct electricity, electrons need to jump to the anti-bonding orbitals or the conduction band from the valence band. If the band gap, or the gap between your valence and conduction band, is too large, like for this example here, then the material will act as an insulator. If the band gap is relatively small, then the material will act as a semiconductor. That is, when irradiated with the correct amount of energy, electrons will jump from the valence band to the conduction band and the material will conduct electricity. Elemental silicon is very famous for its semiconductor properties. For metals, on the other hand, the valence and conduction bands essentially overlap, and electrons get thermally populated into the conduction band. That is what the purple box represents in this final example below. At this point, we will briefly look at the rest of the group 14 elements. Germanium is similar to silicon in that it is a metalloid and a shiny, hard semiconductor in its elemental form. Similar to silicon, it forms tetrahedral species like germane and germanium tetrachloride. Germanium hydrogen and germanium chlorine bonds are even more reactive than their silicon analogs, so they display similar chemistry in the presence of oxygen and water. Here you can see germane reacting with oxygen. And here is germanium tetrachloride reacting with water. Tin and lead, on the other hand, are the metallic elements of group 14. Tin forms mainly tetrahedral compounds, but bent compounds are also known. In contrast, lead forms mainly bent compounds, but can also form tetrahedral compounds. The reason for this difference is due to the inert pair effect. Tin more commonly adopts the +4 oxidation state and thus forms 4 bonds. Lead, on the other hand, adopts the +2 oxidation state more often because these 6s electrons are difficult to remove. When these metals form two coordinate compounds, they are bent because of a lone pair of electrons in the 5 or 6s orbital. Looking at the reduction potentials, we can see both tin +4 and +2 are fairly stable, with tin +4 being slightly oxidizing and tin metal being slightly reducing. Lead +4, on the other hand, is very oxidizing, and lead metal is only slightly reducing. This means that lead +4 is much less stable than lead +2. The last group of the P block that we will look at today is group 5, or the pnictogens. We will first look at nitrogen and then move on to the rest of the group. In its elemental form, nitrogen forms a diatomic gas with a very strong triple bond. This is actually one of the strongest bonds known in chemistry. In order to be used in biological systems for things like DNA, proteins, etc., nitrogen gas needs to first be reduced to ammonia, a reaction that requires the transfer of 6 electrons and 6 protons. This is a kinetically challenging reaction to carry out, and even with catalysts, it requires a large input of energy. We will see how nature reduces nitrogen gas in the final section of the course. Oxidation states for nitrogen can vary between -3 and +5, but the most common oxidation states other than 0 are -3, +3, and +5. +2 and +4 are less prevalent because they are often associated with radical species, as are -1, -2, and +1. Nitrogen compounds are mainly covalent in character with 3 bonds, which gives nitrogen a full octet. Similar to carbon, nitrogen atoms can be sp, sp2, or sp3 hybridized, but unlike carbon, nitrogen also has a lone pair of electrons. So in the pictures below, the 3-coordinate nitrogen or amine would be sp3 hybridized, the pyridine nitrogen would be sp2 hybridized, and the acetonitrile nitrogen would be sp hybridized. The lone pair on nitrogen often defines the chemistry of its compounds, which commonly act as Lewis and/or Bronsted bases. For example, both amines and pyridine are fairly strong Bronsted bases, while acetonitrile is a very good Lewis base. Also, even though nitrogen could conceivably form chiral compounds with 3 different substituents on the nitrogen center, chiral amines do not commonly exist. The reason for this is that amines rapidly invert at nitrogen, similar to an umbrella flipping back and forth. So R and S interchange rapidly at room temperature. For nitrogen in higher oxidation states, these species are commonly associated with oxygenated compounds, such as the nitrate anion, nitrogen dioxide, or nitro groups in organic chemistry, like this nitrobenzene. Most of the chemistry you will encounter with nitrogen has already been covered in organic chemistry. Other nitrogen chemistry tends to be radical-based and is beyond the scope of this course. For the purposes of Chem 712, we will mainly look at nitrate-type spectator anions, nitro groups possibly, amine bases, but mainly nitrogen-based lone pair donors or Lewis bases. Now moving on to phosphorus. In its elemental form, there are several different allotropes. White phosphorus is the most reactive allotrope, which consists of a P4 unit in the shape of a tetrahedron. All the bonds are highly strained, and white phosphorus will burn upon exposure to air. Red phosphorus exists in long 1D chains, where the bonds are far less strained. You can think of red phosphorus as multiple P4 units that have opened up one bond and linked together. So you can imagine if, say, this bond opened up and then these units linked together, you would get red phosphorus. Black phosphorus is the least reactive form and exists as 2D sheets stacked one on top of each other, similar to graphite. The sheets are puckered, however, and the phosphorus atoms are arranged in glucose-like rings in the chair conformation. Just to show you the reaction of white phosphorus in air, you first form this phosphorus pentoxide compound, which violently reacts with water to form phosphoric acid. PO bonds are very strong, so these reactions are very exothermic. Similar to nitrogen, phosphorus forms mainly covalent compounds. Also like nitrogen, phosphorus can adopt oxidation states between -3 to +5, with -3, +3, and +5 being the most common. Unlike nitrogen, however, the other oxidation states for phosphorus are much more stable and prevalent. Most phosphorus compounds are similar to amines in that they are sp3 hybridized with a lone pair of electrons. When naming phosphines, it is very similar to naming amines, except you replace the amine portion with phosphine. For example, if these R groups here were ethyl groups, then this compound would be called triethylphosphine. If they were phenyl groups, it would be triphenylphosphine. If there were 2 methyls and 1 hydrogen, it would be dimethylphosphine, etc., etc. A difference between nitrogen and phosphorus is that these R groups can also be OR groups, like methoxy or ethoxy. In those cases, the compounds are called phosphites and would be named according to the R groups on the OR groups followed by the phosphite. For example, if you had 3 methoxy groups on the phosphorus, so P in bracket OMe bracket 3, that would be trimethyl phosphite. So a very similar naming convention to phosphines and amines, except you replace the phosphine or amine portion of the name with phosphite. We will see phosphines and phosphites quite a bit in this course because they are very good Lewis bases. So they bind transition metals quite well. They are better/softer Lewis bases than analogous amines as well. Unlike amines, however, phosphines are generally fairly poor Bronsted bases because of their softness. Remember that a proton is a hard Lewis acid. Another big difference is that chiral phosphines are well known. So that means if you had 3 different R groups on this phosphorus center here, this species would have isoluble enantiomers. The reason for this is that there is a significant barrier to inversion at phosphorus, whereas for nitrogen the barrier is quite small. Another major difference with nitrogen is that phosphorus is almost never sp or sp2 hybridized and does not readily form double or triple bonds with itself. Can you hypothesize why? It's for the same reasons that silicon doesn't form double or triple bonds readily. It's because the phosphorus atom is much larger, so you do not get effective p orbital overlap in most cases. Looking at some of the reactivity of phosphorus, we can see right away a major difference. While nitrogen trichloride is unstable, phosphorus trichloride is a common laboratory reagent. This is due to stronger phosphorus-chlorine bonds. Despite their relative strength in comparison to nitrogen-chlorine bonds, though, phosphorus-chlorine bonds are prone to nucleophilic substitution reactions with metal-alkyl reagents like Grignard's. This is a common way to synthesize phosphines. Nitrogen-chlorine bonds behave very differently and display a lot of radical character. Chloramines, as they're called, act as very strong oxidizing agents. Phosphorus trichloride also reacts with alcohols to form phosphites, and the driving force for this reaction is the formation of strong PO bonds. Another difference between amines and phosphines is that phosphines are less reactive for SN2 reactions with carbon. You often need to deprotonate phosphines to make phosphides to get the substitution to work. This gives more control, though, over the synthesis of trisubstituted phosphines in comparison to amines, which will overalkylate and form ammonium salts. With respect to the +5 oxidation state, it is much more prevalent for phosphorus than nitrogen due to its more reducing nature. What this means is that the lone pair of phosphorus can be prone to oxidation in air. In particular, phosphine gas, or PH3, is pyrophoric or burns in air because it is so reducing, while ammonia is not air sensitive. Do you notice something different about the bonds phosphorus can make with oxygen in comparison to silicon? It can form double bonds with oxygen. Do you know why? It's because phosphorus is smaller than silicon as it is further to the right on the periodic table, so its p orbitals can more effectively overlap with the oxygen p orbitals. Phosphorus also forms 5 and 6 coordinate compounds with halides. Shown here is phosphorus pentachloride generated through the oxidation of phosphorus trichloride with chlorine gas. Hexafluorophosphate is an example of a 6-coordinate phosphorus compound, and this is a popular anion in inorganic chemistry due to its non-coordinating nature. Moving on to arsenic and antimony, both these elements are commonly classified as metalloids, and they have similar allotropes to phosphorus. The most stable forms of arsenic and antimony are gray and silver respectively, which consist of 2-dimensional sheets of puckered 6-membered rings stacked on top of each other like graphite. The other allotropes of arsenic and antimony are yellow and black, and these compounds act as insulators and are much more reactive. Arsenic and antimony are both more reducing than phosphorus, so they can react with oxygen to form various oxides. Of note is that both of these redox reactions occur more readily with the yellow and black allotropes. When looking at compounds of arsenic and antimony, arsenic often behaves very similarly to phosphorus due to their similar electronegativities. Arsenic very commonly is sp3 hybridized and forms covalent interactions. 5-coordinate arsenic compounds with arsenic in the +5 oxidation state are also known. Due to arsenic's toxicity to humans, however, much less chemistry has been explored with this element. Antimony is less electronegative and even more reducing, so it has more metallic character. It tends to form more 5-coordinate compounds with antimony in the +5 oxidation state, rather than 3-coordinate species with a lone pair. For the purposes of this course, however, we won't talk much about antimony or arsenic. The last element in group 15 is bismuth. This metallic element is a shiny conductor that is stable with respect to oxidation in air. The +3 oxidation state is much more stable than the +5 oxidation state for bismuth. Why is this? This is due to the inert pair effect. Be sure to include what the origins of the inert pair effect are when answering any questions, say in a problem set or on an exam. Because bismuth is metallic and more electropositive, it tends to form compounds with more ionic character than the rest of the pnictogens. For example, bismuth hydroxide, bismuth trichloride, etc., etc. Before we finish today, I want to touch on some applications for the elements in groups 13 to 15 specifically. One important class of compounds from these groups of elements are mixed semiconductor materials. When you think of pure silicon semiconductors, their band gap is an inherent property of the element itself. If you need a semiconductor with a different band gap, however, you need a way to generate materials where you can tune the band gap reliably. One approach that is used is to make alloys of silicon and germanium, and based on the ratio of elements, you can adjust the electronic properties. This approach has some limitations though, as you can only adjust the band gap between that of pure silicon and pure germanium. Another approach is to mix group 13 and group 15 elements such that 3 electrons come from the group 13 element and 5 come from the group 15 element to net overall give you a material with similar properties to silicon where you get 4 electrons from each atom. Some examples include gallium arsenide, indium phosphide, etc. You can also have 3, 4, 5, and up component systems like gallium-indium phosphide arsenide. If you mix the first row elements of groups 13 and 15, boron and nitrogen, then you get analogous materials with similar properties to carbon. Each atom forms 4 bonds, where the 4th bond is formed through a Lewis acid-base interaction. The result of this is that you can form diamond and graphite-like analogs with boron nitride. Shown here is just the diamond analog, but 2D aromatic sheets can also form. Boron and nitrogen analogs of carbon compounds are also known, such as borazine shown right here. The system is aromatic with empty p orbitals on the boron centers and filled p orbitals on the nitrogens. This concludes today's lecture. If anything was unclear, please feel free to ask questions during office hours or try rereading the textbook to clarify concepts. And as always, there are some useful websites and resources in the links below to help with understanding some of the concepts that were presented today.